So hi guys, so far we have seen what happens when, or rather we have calculated what are the maximum number of radiations which are emitted when the electron transitions from the higher state to the ground state, or n equals to 1. So now in this lecture we'll be seeing what are the maximum number of radiations emitted when the electron transitions from higher excited state to a lower excited state rather than the ground state. Okay, so we'll be seeing maximum number of radiations emitted when electron transitions from higher excited state to lower excited state. Okay, so let's see when we have a hydrogen atom. Okay, what happens here is, let's say when we have n1 equals to 2 and n2 equals to 3, electron goes from 3 to 2. Okay, or we can have a situation like n2 equals to 4 and n1 equals to 2. So the electron goes from first 4 to 3, then 3 to 2. Okay, so here maximum number of radiations emitted of different wavelength would be n2 minus n1. Okay, so let's see another case wherein we have sufficient electrons. So in the hydrogen atom, why did we take the hydrogen atom? Because in hydrogen atom we have only one electron. So let's see case 2 when we have sufficient electrons. So in this case we would be having maximum number of radiations emitted as n2 minus n1 multiplied with n2 minus n1 plus 1 upon 2. Okay, so these are the maximum number of radiations emitted. So now let's see maximum number of radiations. So we are seeing the derivations of the above stated formula, that maximum number of radiations emitted, obviously of different wavelength, would be, first we'll be seeing n2 minus n1, then we would have n2 minus n1 minus 1. Okay, it could have left itself out to upper excited state, or excited state with n1 plus 1 excited state. Okay, so till we could have 3 plus 2 plus 1. So this is nothing but n plus n is n2 minus n1, so this is n minus 1 plus n minus 2 up to 3 plus 2 plus 1, so this is nothing but n plus 1 by 2, which would be n is n2 minus n1, n is n2 minus n1 as we assumed here, into n2 minus n1 plus 1 upon 2. Okay, so as you can imagine here, that from 3 to 1 there is one transaction, and from 4 to 3 there are two transaction. Okay, so why is this the case? First is n2 minus n1 is one of the transition here, and then there could also be a transition in which we could have n2 minus n1 plus 1. Okay, so n1 plus 1 would be nothing but third, means number of radiations up to third level, which would be again increasing the count by 1, hence total 4 to 2 would be 2. Okay, but means we can actually also means n2 minus n would be n2 minus n1 would are um, obviously 2 here, and n2 minus n1 plus 1 would again be 1. Okay, so two steps are here, and the third one could be like this, 4 to 2 directly. Okay, so using the formula we are not directly going to the above state of 2, but hypothetically or virtually we are thinking that there could also be a possibility in which we can bypass this and the state just higher to the n1 state. Okay, so that with that I mean n1 plus 1, not really thinking about n equals to 3. We are just hiding this for a second, and we are just bypassing this n equals to 3, or which is n1 plus 1 state. Okay, so n2 minus n1 would be 2. Then we can also have a second one which would be directly bypassing the third one, which is n2 minus n1 plus 1. Okay, so the formula is this. So let's see an example of the same. So example could be, so from 11th to let's say 8th, using the above formula we would get that n2 minus, so let's say it is 5th, so let's to have a clearer and better understanding. So n1 n2 minus n1, this is n2, this is n1. n2 minus n1 is clearly 6, and n2 minus n1 plus 1 would be 7 upon 2, which is 21 number of different radiations emitted by the transition of electrons. Okay, so next let us see one more example on the same, which is you have to calculate the lambda of radiations emitted in terms of R, let's say, or Rydberg constant. Okay, when electron transition takes place from third excited state to ground state, when electron transition takes place from third excited state to ground state of He plus. Okay, so helium originally has 2 electrons. Now helium plus would have only 1 electrons in its orbital. Okay, so using the same knowledge we can calculate that we know the formula that 1 upon lambda is r z square 1 upon n1 square minus 1 upon n2 square. Okay, so it is going from third excited state to first excited state, hence we calculate this that r z is obviously 2, so z square would be 4, 1 upon n1 square is 1, and 1 upon n2 square is 9. Okay, so here we have 1 upon lambda is equals to, so you know that whenever the transition takes place from higher to lower, energy would be emitted. Okay, and this is the wavelength of the radiation emitted. Okay, so 4r, so this term has always to be positive, so you just adjust n1 and n2 and ni and nf that I may have mentioned in some previous lectures. So you can just play around with the minus sign, so that you always have a mod value here. Okay, so nothing that much mathematical here, just remember that it should be a positive value when the electron jumps from higher orbital or higher energy state or excited state to ground state or lower excited state. So it would be nothing but lambda is this is third. Okay, so third excited state is n equals to 4. So ground state is n equals to 1, first excited state is n equals to 2, third is, or rather second excited state is n equals to 3, and third excited state is n equals to 4. Hence value of n would be 4 because this is third excited state. Okay, third excited state is n equals to 4 as n equals to 1 is ground state. So this would be 16 upon, this is again 16 here, 16 upon 60r. Okay, so this is the answer for the question. So with this we come to the end of this lecture. In the next lecture we will be seeing some more examples on the Rydberg constant and the wavelength emitted as a result. So till then, good luck and goodbye.